Alfonso again for lab number 2. Oh, that started on the end. And this lab is motion of a falling object. So to introduce this, we are going to have to go into some physics background. And when discussing the motion of a falling object, we look at two things, or well, more than two things. But in this specific lab, I'm just going to be looking at two things, and that will be the two forces acting on the object, which will be gravity and then drag. And so the force of gravity would be computed, or would only affect the y component of the position vector. So we can count that as negative mg because force equals mass times acceleration. And so you take the mass of the object and then you take its acceleration, which would be gravity, which is 9.8 meters per second. And since you're going in the negative y direction, you just put a negative on it. And then the force of drag, we will be using negative b velocity squared. And b is a coefficient that we will get into later with how we solve for it and stuff. And so the net force on this system will be the force of gravity and the force of drag. And so now we can look at some observed data. So here we have our little video. There's me, and there's the ball going down. Look at that. And so then it created this nice little graph, position versus time, and we can go ahead and take a look at that in Excel. So that would be this one, position versus time. It goes down to there. And now we can look at past the glow script. We can look. No, it would be the glow script. We can look at our code, and so this code will now be gravity versus or an experimental. No, expected. Our expected result. It's simulated. And so this is what we'd expect to get with gravity as our only force acting on the object. And we can see it here. And we've turned it into a little Excel sheet too, gravity only. And then here is our script that would run when we also account for the force of drag. And it is also transitioned here on the Excel script. So to account for, or to create these programs, we basically reverse engineer our X direction ones from 2 weeks ago. And so we do that by making sure our j hat is pointing no, it's not pointing anywhere, but that it's only affecting the y direction, so that we can account for that motion of the object. And then we now have to use some different FNet formulas, which will be the ball's mass times gravity, and then in the j hat direction, which will be down this time. And then our ball's velocity update will be its initial velocity, which is 0, and then we add FNet divided by the mass, and then we multiply that by delta t. And FNet, of course, as we mentioned, is just gravity in this one. And then position update is just the velocity times delta d t plus the initial position. And yeah, there's nothing special about that code. We've seen it before. But on this one, where we're also accounting for the force of drag, we have to do a little bit more maths. And that would be with our b. Our b, I rounded it, but you have to reverse engineer. Let me scroll up. This equation to solve for b, because we know from our graphs that we took, we can approximate what effect the drag had on our gravity, because of course these two are different. And then so you know what the force is, all of that, and so you're able to substitute into everything but b to find b. And so yeah, that's how I solve for it. And then we now have to change our net force equation because our net force is now two components, gravity and drag. So you just add those two together. Those two make up your FNet, at least in the y direction. None of the other equations change. And then as we saw, it just creates this little thing. So Excel was being a pain, and it did not let me put my graphs together for some unknown reason. So I created this small little paint comparison, and that's just so that then we can see the difference. So I'll go ahead and be the key with my little cursor. This is the this one right here is our expected position versus time graph based on just gravity. This one right here is our expected position versus time graph with gravity and drag acting on the object. And then this one right here is what we got experimentally. And so as we can see, because drag will slow the object down, it is going to be higher. Its position is going to change at a slower rate than gravity, than if gravity were just acting on it alone. And then our experimental one, the one that we observed, that one just shows that there could be some issues with human error, or that we didn't account for all the forces, like the air density, for instance, things of that nature. Just we could go on and on about that, but I won't. So now some questions. Terminal velocity would let's pull up the question. So what does it mean? Terminal velocity is just when the force of drag is equal to the force of gravity, and that makes net force 0, because if your gravity is, I don't know, negative 9.8, but your drag is 9.8, then that's like newtons, then they're both going to be 0. And then what if the object was thrown down with some sort of initial force? So we can go ahead and quickly model that by just editing the program and then changing its initial velocity. Let's make it -1. It started with -1 force. And then when you run it, you will see that you get the exact same thing. It just goes there a little faster. Terminal velocity will make it so that it stops at that speed no matter what. So it will reach the same terminal velocity. It just makes it there faster. That's all there is about it. And then we get to the beautiful the end slide. The end, people. Good job. Have a nice week.